Welcome into our video on integration by parts. Right, so it's an integration technique that we're going to need moving forward. And let's go ahead and just write out the equation and we'll uncover where it came from. Okay, so the equation as follows is the integral of u dv is equal to uv minus the integral of v du. And many of you have the right idea. Where is this coming from? So let's try to figure that out. Right, we're going to recall all the way back from Calc 1, right, the product rule. So if I have two functions, and again, you're probably wondering how do these connect? You'll see it, don't worry. We have fg, and we're going to take the derivative of f and g. This is going to be equal to, we'll say f prime g, plus, we'll keep f, and we'll take the derivative of g. All right, so this is just the product rule. Both of these are functions of x. I'm just shorthanding it for right now, but in a second I will write that out. Okay, so now let's say I've done this, and I want to integrate both sides. All right, so I'm going to go ahead and integrate fg prime with respect to x, and we're going to integrate the other side. F prime g plus f g prime, again also with respect to x. Okay, and let's see what happens. Well, a little bit of fundamental theorem of calculus here. If we take the integral of the derivative, right, it all goes away. So we just end up with f and g over here, right? F and g. And this is equal to, well, we're going to distribute this integral sign, right? This is we're allowed to do this. So we'll distribute f prime g dx plus the integral of f g prime dx. Awesome. Okay. Now what can we do? Well, we're going to do a little bit of rearranging. That's all we're going to do. We're pretty much done. I'm going to leave the fg prime over here, and I'm going to move f prime g to the other side, but I'm going to write it flip-flop form. So this is going first. I'm writing the right side first, so it will match up here. And so it looks like the integral of f g prime d of x, and again, both f and g here are functions of x. I'm kind of being lazy and shorthanding it, but we'll see how it all connects in a second. This is equal to fg minus the integral of f prime g dx. Maybe take a second, pause the video, stare, make sure that we see all I've done is move this piece to the other side and set them equal to each other. And now we really do have exactly what we need. These are equivalent, right? They've always been equivalent, but the point is, all we're doing now is just some relabeling, right? So let's go ahead and relabel, right? So we're going to say, let's go ahead and let u be equal to f of x, which means that du, the derivative of u, is equal to f prime of x dx. Awesome. Okay, and we're also going to say, well, let's go ahead and let v be equal to, let's do g of x, which means that dv is equal to g prime of x dx. Okay, and now all we're going to do is substitute everything out here. Let's just go down the line starting from left to right. F, u, right? F is u. So we'll write the integral of u, right? G prime is going to be dv is equal to fg uv minus the integral of f prime, which is du, and g, which is v. So I'm going to write it in this format, v du. right? And we've uncovered everything that we need to do here. Right, now I'm going to write a very brief example just so we can see, but we're going to go through this example in the next part of the video. So a very brief example here is, let's say f of x is equal to x e to the x, right? And what should strike a nerve here is the fact that we uncovered this using the product rule. So if we see two functions being multiplied together, maybe in our head it might click that we should look for, this is integration by parts. Okay? Now, maybe you ask yourself, well, how do I know which one to be u and which one to be v, right? Or dv, right? So in this case, you're setting one of them to be u and the other one to be dv, right? So the question is, how do I know which one's which, right? And the key thing that you want to look at here is this over here, this du, right? So in my integral, right, I have a du, so meaning I should set my u, right, to be the piece that makes my integral easier, right? It makes my integral easier. So in this case, if I take the derivative of x, what does that get me? Well, that gets me 1, right? That's a very nice number to put over here. So that's where we're going towards. Again, I don't expect everyone to grab this on the first try. That's why you go through many examples that we will see in the previous in the videos following this, right? But just so we know, this would be u, this would be our dv, and this is kind of the only hard part, right? The hard part is knowing which one's u, which one's dv. Once we have that, there's a very algorithmic way of going about this problem. Okay, so I will see you in the next part of the video. We'll go through this exact question, and we will do a few more. So see you there. All right, let's go ahead and we're going to jump into a couple examples. So we're going to do the one that I just had up. First, let's go ahead and compare and contrast. So we have example number 1 over here. And this is going to be the integral of x e to the x dx. All right, so we'll keep that there for a second. Right, think about which one we want to set to u. I gave it away in the prior part if you skipped it. And over here, we're going to say, let's write it, I need more room with example 2. We're going to say example 2 we're going to say the integral of 3t, and I'm using t's instead of x's, but who cares, right? We have an independent variable, that's all that matters here. Cosine of t dt, right? Two indefinite integrals. Right, so again, doesn't matter if I use x's here and t's here, right? As far as integrating, we have the same rules. Okay, so again, what are we really looking at? We have a function times a function in each one of these. We want to pay attention to which one of these, when I set it equal to u, right, from our equation, will give us a nicer, let's say value, and I don't want to say value, but a nicer function to deal with in our integral, right? So we want to pick u to be the one that helps me the most. So in this case, let's say u is equal to x, which means du is equal to 1, right? The derivative of u is du, the derivative of x is 1 dx. And I would line this up just as such, right, to keep all your information organized. Okay, so if I pick x to be my u, that means e to the x must be my dv. And now if I integrate both sides, so if I integrate dv, I'm going to get v. And if I integrate e to the x dx, I get e to the x. Perfect. Okay, so again, now we have all the pieces to our puzzle. Let's reference our equation, right, for integration by parts, and we can just put everything together. So let's see what happens. So I'm going to write it out in full. We know that u dv, right, is equal to uv minus the integral of v du, right? So this is the whole reason why I chose u to be x, because look what happens. This is v du. Look how nice this integral is over here, right? here we had x e to the x, now we just have an e to the x. We know how to integrate that. There's no problem involved there, right? So our final answer is x e to the x minus the integral of e to the x. Well, that's just e to the x. And what do we never forget with our indefinite integrals? Plus c, right? So this is very important. I know I mention this all the time, but plus c, right here, this is one answer. This is infinite answers, right? One answer, infinite answers, right? So plus c is very important. Let's go to example 2. So again, we want to take that same idea of what should we set our u to be that will make life easier down the road? Maybe pause the video. You didn't pause the video? Okay. So u is equal to, we'll do 3t plus 5, which means that du, right, the derivative of u is just going to be 3 dt. Perfect. Okay. And what's next? Well, that means if u is 3t plus 5, that must mean that dv is equal to cosine of t dt. Right, if we integrate both sides, the integral of dv is going to be v, the integral of cosine of t. Where does a positive cosine come from? You are correct, sine of t. There we go. Okay, again, we have all the pieces to our puzzle. Let's put it all together. Now I'm gonna, because I'll run out of space, this is our u dv. So I'm just gonna write out the right side. Right, the right side of our integral here is gonna be equal to uv. So this is u, v, sine of t, minus the integral. So again, why did I pick my u to be 3t plus 5? Well, when I take the integral here, right, I got this nice value of 3. So v du, I end up with 3 sine of t dt. And now we can do a little bit of algebra, right? A little bit of simplifications first, right? The 3 can go on the outside of the integral. There's no reason for it to be in there. However, yeah, that's fine. I know we're rewriting a whole step just to do this, but it's just good practice because somewhere down the road, it'll make life all the easier and we won't be confused. I almost did it again. 3, we'll put 3 there. There we go. Sine of t. And so now the question we need to ask ourselves is, again, notice the difference here between the integrals that we need to solve. The integral here was this ugly thing. The integral here is just a sine of t. Right? Where does a sine of t or a negative sine of t come from? Well, it comes from a positive cosine, right? So at the very end of all this, this is 3t plus 5 sine of t. And instead of a minus, right, a negative sign comes from a positive cosine, so plus 3 cosine of t. And again, what do we not want to forget here? This is one answer. We need infinite answers. Awesome. Okay. All right, so hopefully these 2 examples helped. I do have 2 more for you, right? We'll go through one the same way we went through it. It'll be a little bit different dealing with ln of t, and then we'll use a different method that might be helpful called tabular. So I will see you in those 2 parts of the video. Let's go ahead and jump into our 3rd example, right? So 3rd example, we're gonna write this out, right? So let's write out example 3. Very important. Example 3, we're going to have the integral of x squared natural log of x, we haven't seen this, dx, right? Now the whole mystery with these problems, right, and the equation should pop up just in case we forgot it, is what do we set our u to be, what do we set our dv to be, right? And so far, right, it's been pretty predominantly like we look at the x, right, the x that's by itself, and we set that to be u, and that makes life easier. So maybe that's our first guess. right? We go, well, you know, it's worked out in the past. Maybe it'll work out again. I go u is equal to x squared. Looks great. I take the derivative. Easy enough. 2x is easy to work with, right? Okay, well, if that's going to be my u, then it must be true that my dv, right, has to be equal to the natural log of x dx. Okay. And I go, well, I know how to integrate dv. It's obviously v. We've been doing this for the last 2 times. It's practically second nature. And I go, well, let's take the integral of ln of x. And then I stand there and I go, we can't do this. We're stumped, right? We don't know what the backwards of ln of x is. I have no idea. We know what the derivative of ln of x is. Don't confuse the two, right? But I don't know how to get in the backwards direction. So we're going to cross this out. And we're going to develop this rule here that anytime we have natural log of x, it's going to take precedent, and this is what's going to be our u, right? So if you have a natural log of x, that's what you need to set u to be, because I don't know the integral of ln of x unless I'm going to use another integration by parts. Right, so we'll leave this here as an example of what not to do. And we'll come over here, now that we know this rule, let's go ahead, we'll just set this up. That means u is going to be equal to the natural log of x. And again, we do know the derivative of this. Du is going to be 1 over x dx. Awesome. Okay, so that must mean, if u is natural log of x, that must mean dv must be equal to x squared dx. And this is not too bad to integrate, right? This is obviously v. And we're doing the backwards power rule. We add 1, we divide. I'll write it as such, x cubed over 3. Right, that's not bad. Okay, now let's take this and use our integration by parts formula, which should be hanging out down here. And we'll say, well, this is going to be, right, the integral of u dv, so I'm just going to rewrite it one more time, dx is equal to uv, right, uv right here, perfect. And I'm going to write the 1/3 out here just so it looks formatted a little bit better. uv x cubed natural log of x minus the integral of v du. Okay, well, let's see what happens here, because this is kind of where everything needs to take place and make life easy for me. I have x cubed over 3, right, uv minus v du times 1 over x dx. Well, what happens? That actually does look very nice, right? I have some x's that are going to cancel each other out. And then we'll leave this here. I don't need to copy this down. So we have 1/3 x cubed natural log of x minus, what does this simplify to be? Well, let's pull out the fraction here. We have a 1/3. And we have our integral. I know I'm going into my other integral there. That's fine. I have these x's that'll cancel each other out. And this should look very familiar. X squared. Didn't I just do that? I just did that. So now we're just going to repeat the process one more time. Right, so I'll write it down here so I don't overlap again. So our final answer is going to be 1/3 x cubed natural log of x minus, well, let's pay attention. What happens here? We're going to add 1, divide by 3. Right, so this is going to be x cubed over 3, and we have another 1/3 here. Right, so I know I'm doing steps all in one motion, but again, x cubed over 3 is what this integral will turn into, times another 1/3. Right, so this ends up being 1/9 x cubed. And this is one answer. How many answers do we need? Infinite answers with an indefinite integral. Awesome. And I purposely do a bigger c just so we get the point. Don't forget the plus c. Okay, so hopefully this example helped. Again, kind of a rare situation, but if we do have a natural log of x, that is the one that has to be the u. Right, and then we get this very nice case where we should have some sort of cancellation, right? So natural log of x takes precedent. We set that to be u. X squared becomes our dv. Not that bad of an integral to do. We end up solving, don't forget your plus C. I will see you for one more example in which we will use tabular in order to avoid a double integration by parts. I will see you there. Okay, so I might have lied a little bit. We got to wait one more video to do tabular. I do want to show the double integration by parts only so we can compare the procedures between double integration by parts and tabular. So let's go ahead. We're going to jump into example 4. We'll use some valuable board space to write out what we're obviously doing. Okay, so this is going to be the integral of x squared cosine of x dx. Okay. Right, so let's just jump into it the same way that we normally would do, and we'll uncover, right, the problem with this as we go. Okay, so let's say we go ahead and set u equal to x squared. Seems fine, seems easy enough. The derivative here is equal to 2x dx. Okay, so far so good. Nothing wrong with this, which means that dv must be equal to cosine of x dx. And we know how to integrate dv, it's obviously v, and we know how to integrate cosine of x. Where does a positive cosine come from? You are correct, it comes from a sine of x. Awesome. Okay, so what's the issue? We got all the puzzle pieces, let's just put them together. Right, I'm just going to write the right side of our equation, right, which is going to be uv. So this is equal to uv, right, sine of x, minus the integral of v du. Okay, what's the problem? This doesn't look good. Because what was the whole point here? The whole point of doing integration by parts was to make this integral over here look nicer, right? This integral here was supposed to simplify and be nice for us to integrate. However, we still have another function multiplying by a function. What does that mean? You guessed it, integration by parts one more time, right? So it'll seem a little bit weird because we're going to label some more u's and v's here. Right, now we got to make sure we keep track of this negative sign too. That's a common mistake that happens. So let's say u is equal to 2x, which means, of course, du is going to be equal to 2dx. Okay, so now we can kind of tell this is going to be helpful because the du ends up on the other side of that integral, right? And a 2dx is very nice to work with. Okay, so this should be good. Okay, if u is equal to 2x, that must mean dv must be equal to sine of x dx. And of course, we know how to integrate dv. This is obviously v. And where does a positive sign come from? You know it, cosine, negative cosine of x. Right, so again, we have all of our puzzle pieces part 2. Let's go ahead and jump over to setting all this up, and we're going to rewrite it out. So starting with our very first term, don't forget about it because we still need it. Right, so this is now equal to x squared sine of x minus, right, minus, and now in brackets or parentheses, whichever you prefer. Right, we have uv again. So this is going to be 2 times a negative cosine of x, right? So negative 2x, let's make sure I'm not messing anything up. Awesome, 2x cosine of x minus, right, the integral of v du. Well, the good news is now when we do v, we have a negative sign and we have a negative sign. We can make this a positive sign, and we have 2 cosine of x dx. And we will end that bracket. Perfect. Okay, so now finally, right, let's go ahead and we can start writing this all the way out. So we still have to remember a few things. We have our x squared sine of x. Perfect. minus, we'll deal with this later. Let's just go ahead and actually do the calculus part here. We have negative 2x cosine of x plus, where does a positive sign come from? You guessed it, right? Positive cosine comes from a positive sign. I answered it for you. 2 sine of x. And I'm just going to put the plus c on the outside, right? It's plus c. Perfect. Don't forget the plus c. Okay, now let's just distribute this negative sign, and we'll see what we end up with. All right, so our final answer, x squared. All right, it feels like we've been doing a marathon with this problem. Sine of x, double negative, plus 2x cosine of x. We're almost there. Plus 2 sine of x. And this is one answer. We want infinite answers. Plus c. Don't forget the plus c. So again, this problem takes quite a bit of time. Now, what do we notice here? What is the relationship? Right? How would we know ahead of time this is going to be a double integration by parts? Right? The dead giveaway here for double integration by parts is going to be this 2, right? The fact that this is a 2, I know that when I take its derivative, it goes to 2x, and then I have to take the derivative again to get this to be this nice 2 over here on the other side of my integral. So I know it's going to be a double integration by parts. You can imagine if it was raised to the 3rd power, 3 integration by parts. If it was raised to the 4th power, 4 integration by parts, right? So this could get out of control really quickly, right? 2 integration by parts took long enough. Again, we go through the process, we set it up. Now that we've seen this though, I want to go through tabular, right? So I will show tabular in the next part of the video. Some of you will be very upset that I made you go through this, but it'll be okay because sometimes this will not work, and I will talk about sometimes tabular will not work. So I will talk about when tabular does not work. I will see you in the next part of the video. Now, the moment everyone's been waiting for, tabular. Right? Okay, so I'm going to write up this same integral that we've been doing. I'm going to take up the middle of the board because I don't think it'll take up... we'll go over here just in case. All right, we're going to do the same one we just did in double integration by parts. Okay. Now, tabular, also known as, I think, the DI method, as told to me by one of my students, right, can only be used when one of these functions, right, so one of these functions, either x squared or cosine of x, one of these functions has the property that as you take the derivative repeatedly, over and over, one of them will go to 0. Right, well, cosine of x, if I keep taking the derivative, I'm going back and forth, cosine, sine, etc., negative and positive. X squared, though, as I keep taking the derivative, what do I get? X squared, 2x, 2, 0. All right, so that tells me that I can use tabular, right? One of the functions, as I keep taking its derivative, has to go to 0. If we don't have either function that does that, we can't use tabular, right? So that has to be true. So, in order to set up tabular, I'm going to write over here, this is why I guess it's known as the DI method. One of them, I'm going to take the derivative, and I've already stated which one I'm going to take the derivative. I've said x squared, but I'm going to wait for a second. The other one, I'm going to take the integral. So one, I'm going to keep taking the derivative repeatedly. The other one, I'm going to keep taking the integral. Okay, so let's write out. I said for the derivative, I'm going to keep taking the derivative of x squared. So let's just write all of them out in a straight column here. I have x squared, the derivative is 2x. The derivative of 2x is 2. The derivative of 2 is 0. We are done. Once we hit 0, there's nothing else for us to do. Over here, I'm also going to label that we switch signs. Plus, minus, plus, and minus. We really don't need that last one. That's okay. All right. So one of them, the x squared, I took the derivative. I'm done. The next one, cosine of x. I'm going to keep taking its integral. So where does a cosine of x come from? It comes from a positive sign. Where does a positive sign come from? It comes from a negative cosine. Where does a negative cosine come from? You guessed it, it comes from a negative sign. And we are done. All right, so once we are at this point, all we're going to do is make some diagonals. And we have solved our problem. All right, so rather than do double integration by parts, we now have our solution. We're just going to multiply our diagonals here. We have a plus sign to lead. So this is equal to x squared sine of x negative negative, so plus 2x cosine of x plus minus 2 sine of x. Plus c. And that is it. We are done. All right, so way quicker of a method. Again, we can only use this when one of the functions, as we keep taking its derivative, goes to 0. In this case, the x squared, right? X squared, 2x, 2, 0, start at cosine, goes to positive sign, right? Comes from a positive sign to a negative cosine, comes from a negative sign, right? We are cross multiplying these values, or we'll say diagonally multiplying, right? We put them all together, we have our answer, right? So again, make sure you know when to use tabular. Hopefully you can use it instead of double integration by parts, but just make sure you're double checking. So that is it for this video. Thanks for sticking around. I will see you in the next one.